All right. Fred, whose mass is 75 kilograms, jumps upward from the top of a platform with a vertical speed of 4.5 meters per second. The platform is 2 meters above a trampoline, which is below. And we're going to answer some questions. So first of all, how fast is Fred traveling when he lands on the trampoline? So there are certain things that we could say immediately. Although in the real world there is such thing as air resistance and drag and friction, we're going to make the approximation that we can ignore it. For one thing, it's not mentioned in the problem, and secondly, at the slow enough speeds that Fred is moving, we can safely neglect air resistance. So the first thing that I want to do is just say that we're going to model the neglect of air resistance, friction, and so on. I also noticed that the kind of forces that we have here, once Fred has left the platform, we have the force of gravity acting, and then we'll have a spring force. And both the gravitational and spring forces are nice in the sense that they are conservative forces. And so, when I start to think about the concepts that may be needed here, I might write down forces, and if I write down forces, I might write down Newton's laws. I also have conservation laws. In other words, I might want to think about energy and its conservation. Okay, so we have a model, we have our concepts, and we might want to think about the relevant equations that we would have. The equations that correspond to conservation of energy, COE, is that whatever the initial mechanical energy is, it'll be equal to whatever the final mechanical energy is. Okay? What is the mechanical energy? We have to remember that the mechanical energy, E, is the sum of the kinetic energy and the potential energy, or potential energies if there's more than one. So to apply this, therefore, those two equations will tell us if the initial and final mechanical energies are equal, then the initial plus the initial kinetic and potential are equal to the final plus final. It's not that each one individually is conserved, it's that their sum is conserved. So that is going to be a guiding equation that we will attempt to use here, and we'll see if we can make some progress. Now, we have a picture, but we probably also want to indicate what are the coordinates here. We get a choice in doing so. So I'm going to set up some coordinates. I'm going to let this be the y direction, and we will mark here what I'll call y naught, which will be the initial position of Fred, which I'm going to call that h just for now. That's the height that he is above the trampoline. Let's call that h. And when he lands on the trampoline at a final height, let's call that a position 0. We also know that Fred leaves with an initial velocity, which is given. It's given as 4.5 meters per second. And also the height is known as well, and we know his mass. And so there's all these things that we know. We know the mass to be 75 kilograms, we have the initial speed, and we also have the height of 2.0 meters. And we also know that we're presumably on Earth, so in case we need that, we can just note that we're going to involve a g for the acceleration due to gravity, and that's 9.8 meters per second squared. So let's see if we can combine these ideas with this conservation of energy. The initial kinetic energy is given by whatever Fred is doing at the very beginning. That's 1/2 times his mass times the initial speed that he has, plus the initial initial potential energy that he has. There's a formula for that. In fact, let me write that back over here. The formula for gravitational potential energy obeys the generic form mgy, where y is the vertical position. The way that we've set things up, we can call this m times g times h, okay, if we're putting 0 at the height of the trampoline. At the very end, after Fred has gone up and come back down, he will be landing on the trampoline and have some final speed, which I'll call v final squared. So at some later point in time, when he's at this position, he's headed downwards with some final velocity vf. And at that point, what is his potential energy, mg, and the final height, which is 0. I'm just writing it there to be explicit. So that term will vanish, and we can start to clean things up. Notice that, yes, this term vanishes because that's 0, but there's a mass term in each of those terms in that equation. We can divide by m everywhere. In other words, that mass cancels from the analysis. We could multiply through by 2 and take a square root. What that's going to tell us is that v naught squared plus 2gh with a square root should give us the final speed. So the velocity would be plus or minus that, but the speed is just the magnitude. We can now plug in our numbers, and when we plug in the numbers that we have, the initial speed, g, and the height, we will determine that this is equal to 7.71 meters per second, which I'll go ahead and round to 7.7 meters per second. That will be the final speed upon hitting the trampoline. Now, in part B, what we're trying to figure out is if the trampoline behaves like a spring, then when Fred hits it, he will start to depress the spring and go down, go down, go down until he hits the bottom that it's going to be. Let's draw a little diagram so that we have a sense of what that's going to look like. In black here, let's put the trampoline just as Fred is coming down, making contact with it. And then later, when Fred is at the very bottom that he's going to be, he's brought it downward. Here he is. Okay? And let's put our axes in so we can really be sure that we know where things happen. This here is what we're going to call 0. That, for purposes of doing part B, we could consider that to be the initial y position. So, in other words, we can call that the initial y position is equal to 0. Where does he end up? Well, we don't know the value of that, but that's what we're going to call the final value. And in fact, if we can figure out what that number is, that will tell us the answer to the question. What else do we know? We know that Fred is coming down with some initial velocity. Keeping in mind, this is the initial velocity that we figured out from part A. So this initial velocity is going to be that number, 7.71 meters per second. And it's going downward, so technically I should call this minus 7.71. At the end, when he gets to the very bottom, his final velocity will be 0. And that's a number that they didn't tell us, but it's something we have to infer from the physics of what's going on. Okay, is this enough information to take it further? Well, we know that we only have a gravitational force and a spring force present. Those are nice conservative forces. And so we'll continue to use conservation of energy, which I'll remind us looks like this. The initial kinetic energy plus the initial potential energy should be equal to the final kinetic energy plus the final potential energy. And this is where we have to be extremely careful because we have two forces to deal with. We have gravity and the spring force. Kinetic energy at the beginning, 1/2 mv naught squared. The gravitational potential energy at the beginning is m times g times 0, so that term will be 0, plus the spring potential energy. Because we have a trampoline that behaves like a spring, let's remind ourselves that the spring potential energy formula looks like this: 1/2 times the spring constant k times the displacement of the spring from equilibrium. And I might call that delta x or delta y. Because we're talking about stretching and compressing in the y direction, I'll just call that delta y. So this term would be 1/2 times k and times 0. It's actually 0 because at this moment, at the beginning, the trampoline has not been depressed at all. So it hasn't been moved from equilibrium. Now, all that contributes to the initial energy. Now, in the end, what do we have? We have 1/2 mv final squared. Well, that's 0, because that's when Fred is temporarily at rest. Plus mg y final. It's a different height. And then lastly, what is the spring potential energy? It's 1/2 times k times the final y position minus the initial y position, which was 0. And that is now accounting for all the kinds of energy that we have. We have taken account of everything, and now let's simplify our life. We'll get rid of everything that is 0, so these 3 terms, and let's just summarize what we have. We have 1/2 times mv naught squared. That's equal to mg y final plus 1/2 k y final squared. Taking a look at what we are given, we know what m is. V0 we've already computed in part A, so we have this. We have the mass, we have g, we have k as well. This value is k. Therefore, the only thing that we don't know is y final. Unfortunately, this is going to be a quadratic equation, so you will have to use the quadratic formula probably to solve this. When you rearrange, you will solve for y final using the quadratic formula. And if you plug in the values given, what you'll get is two possible solutions. Remember, the quadratic formula tells you that there's a negative b plus or minus a square root term. There are two options, therefore. You'll either get this as 0.29 meters, or you'll get it's a positive 0.26 meters. Just thinking about what's going on here, Fred started at a height of 0 and depressed the trampoline. Therefore, we expect y final to be negative. That means that this must be our final answer. It ends up at a final value of negative 0.29 meters. In other words, that it depresses by, and now we can just say the absolute value of that number, it depresses by 0.29 meters.